Today I will introduce the subject vector space. After a brief discussion on the fundamentals of the subject, I shall cover some of the definitions and one theorem. Any space containing a set of vectors is called a vector space. It may be a real space or purely a mathematical space. The vectors present in the vector space follow the usual rules of vectors. First rule is that vector addition follows commutative law, which means ordering of vectors is not important in case of addition. Second rule is that vector addition follows associative law. In case of addition of three vectors, which are added first is irrelevant. As demonstrated here, the first and second vectors are added first and then their resultant is added to the third vector and get the resultant for the addition of these three vectors. Now let us follow a different way where the second and third vectors are added first and then their resultant is added to the first vector to get the final resultant. As it can be seen, following these two ways, we end up with the same final resultant vector. The third rule is the distributive law. Taking the scalar multiple after adding two vectors is same as taking the scalar multiples of the vectors first and then adding. As demonstrated here, the resultant of two vectors is multiplied by 1.5. Alternatively, each vector is multiplied by 1.5 and then these scalar multiples are added. The result is same in both the case. There are also rules for distributive law of two scalar multiples and associative law for multiplication. A vector space is linear if it obeys certain rules. If scalar multiples of any two vectors in that space are added, then the resulting vector should also belong to that vector space. In the vector space, there must exist a unique null vector such that the addition of any vector belonging to the space to this null vector does not change the vector. Corresponding to every vector in the vector space, there exists a unique inverse also belonging to the same space such that when the vector and its inverse is added, it results in a null vector. If any of the vector is multiplied by 0, it will give a null vector. Any vector multiplied by unity results in the same vector. It is important to note the types of scalars that can be taken for a specific linear vector space so that it obeys the rules. This is called the field over which the vector space is defined. Now I will explain the linearly independent vectors. First, let us consider a vector space that contains a set of vectors. Now it is possible to combine two or more of these vectors following the rules of vector addition after multiplying them with suitable scalars in such a way that these vectors cancel each other. Mathematically, this process can be written as this expression. In this way, one by one, the vectors can be eliminated. However, some vectors cannot be eliminated and will remain there. The only way to eliminate these remaining vectors is to set the value of the scalar alpha I as 0. In case of a two-dimensional space, like the display screen over here, two such vectors will remain which are perpendicular to each other. These two vectors are called linearly independent vectors. In case of a three-dimensional space, maximum three such linearly independent vectors will remain. Similarly, in an n-dimensional space, maximum n numbers of linearly independent vectors will remain. In this way, we have found that the maximum numbers of linearly independent vectors that can exist in a vector space defines the dimensions of that vector space. Now I will discuss a theorem on vector space. The statement of the theorem is that an arbitrary vector v in an n-dimensional vector space can be expressed as a linear combination of n linearly independent vectors in that vector space. To understand the theorem, let us assume a five-dimensional vector space. It contains five linearly independent vectors. Let us name them as v1, v2, v3, v4 and v5. According to this theorem, any arbitrary vector, say v, in this space can be expressed as a linear combination of these five vectors. Mathematically, this can be written as the sum of 5 alpha I vi's. In order to prove the theorem, let us consider a relation in an n-dimensional vector space. Here, vi's are the linearly independent vectors and alpha I primes are the corresponding scalars with which each of these vectors are multiplied with. V is the arbitrary vector and alpha is its corresponding scalar. From this relation, we can easily write V is equal to summation of alpha I vi, which shows that V can be expressed as a linear combination of vi's. But as you can see, in the intermediate step, we have written alpha at the denominator. We can do that only if alpha is not equal to 0. Therefore, in order that this step is valid, we have to ensure first that alpha is not equal to 0. We will do that logically now. Let us recall here that an n-dimensional vector space can have at most n numbers of linearly independent vectors. Now in the relation that we considered, if both alpha and all the alpha I primes are zeros, the second term indicates n numbers of linearly independent vectors and the first term indicates one linearly independent vector. Thus, in total, there are n plus 1 numbers of linearly independent vectors, which is not true because we are dealing with an n-dimensional space. Hence, sum of the alpha I primes must be non-zero. Next, what if alpha is equal to 0? We can see if alpha is equal to 0, the first term goes off. What remains is the second term only, that is alpha I prime vi is equal to 0. However, we have already established that some of the alpha I primes are not zeros. By virtue of this fact, if you can recall the definition of linearly independent vectors, not all the n numbers of vi's present here are linearly independent, which is again not true because we are dealing with an n-dimensional vector space. Thus, we see that assuming alpha is equal to 0 leads us to a wrong conclusion. Hence, it must be that alpha cannot be equal to 0, or in other words, alpha is not equal to 0. And in this condition, we have already showed that any arbitrary vector v can be expressed as a linear combination of linearly independent vectors. The theorem also states that the linear combination is unique for any arbitrary vector. This means that any specific vector can be expressed in only one way of combination. We shall probe this fact now. Let us take this arbitrary vector v and express it as a linear combination of n numbers of vi's. Although the theorem states that only one unique combination is possible, let us disregard the theorem for the time being and assume that a different linear combination is also possible. Here we replaced all the alphas with betas. Subtracting one relation above from the other, we get this. Here, vi's are the linearly independent vectors. Now recall the definition of linearly independent vectors according to which this must be equal to 0. Hence, beta must be equal to alpha. It is thus demonstrated that even though we assumed a completely different set of scalars, betas, in place of alphas, we end up with the fact that this beta is equal to alpha. This proves the uniqueness of the combination. Since any vector can be expressed as a linear combination of these linearly independent vectors, they are also called basis vectors. Now, in order to really appreciate the utility of this theorem, I shall give you an example in a domain that you students are more familiar with. Take the example of a three-dimensional vector space that is easier to comprehend with. Since it is three-dimensional, the space will have three linearly independent vectors. These are usually named as I, j, and k. Take v as an arbitrary vector. As per the theorem that we just discussed and proved, this v can be written as a linear combination of these I, j, and k, which are the basis vectors for a three-dimensional space. Alpha 1, alpha 2 and alpha 3 are scalars that are called as components of V in three dimensions.